Okay, good morning, everyone. Today we will solve a couple more examples for series parallel analysis technique, and then we'll look at voltage and current division, and then the last 10 minutes we'll introduce the new topic of node voltage and mesh current analysis. Okay. Before we begin, I want to ask, how many of you know how to use MATLAB? Several of you. That's very good. You probably I'm not an expert on MATLAB by any means, but to all students, I would like to advise that MATLAB is a very powerful computational tool for engineering, especially for engineering. It uses, it is used in all fields of engineering, but especially true for mechanical as well as electrical engineering. If you go online and look at any job postings in your field, chances are more than 50% of those listings would have MATLAB as a required skill, or at least if it's not a required skill, it will at least be like a, if it's not required, they would say at least it's good to have on your resume. Okay. So in this class, this is not a MATLAB class, but what I would advise students to do is you download MATLAB from their website. Cal Poly has an institutional license, so all it's required is your email ID, Cal Poly email ID and password, and you can activate a license on your computers, laptops, desktops, tablets, smartphones. I have it on my laptop as well as on my smartphone. And when I first started, we didn't have MATLAB when I first was a student. So when I started learning it, literally the first thing I typed in there was 2 + 2. I'm not kidding. That was the first thing I typed in there. And just start learning it. Well, learn by doing it. So again, it's not a requirement for this class, but you can use those to solve linear equations. You can use MATLAB to solve equations for complex numbers, right? And as you build up your skill set, by the time you graduate, hopefully you know enough to put it as a skill on your resume. Okay. All right, so let's begin. We will go to the example for series parallel analysis. Section 3. And let me share. Okay. So 3 examples. We look at all 3 of them. Won't solve all of it, but let's take a look at A. Series parallel analysis requires as the first step that you remove the source from your analysis and you determine Req from the perspective of the source. In this example A, source given as Vs, 20 volts. We remove Vs from our analysis, redraw the circuit, and calculate Req. Again, from the perspective of the source, right? Perspective of the source. So what do we see? When you want to find Req, we go at the farthest end and you move towards the terminals of measurement, reducing the circuit step by step, one at a time. What do we see? R4, then R3, and then R2. Both ends of R4 are connected to both ends of R3, and they're also connected to both ends of R2. So they are in parallel. And then let's call it R5. R5 is the parallel combination of R2, R3, and R4. There's R1. So my Req is simply R1 plus R5. R1 and R5, again, R5 is a mathematical representation of the 3 resistors in parallel. R1 and R5 are connected at the top node, and so they are in series. Req is simply R1 and R5. For explanation purposes, I'm going to draw this out. So you have VS, you have REQ. What is REQ? Calculator's out, and you tell me 10.1. Let's see what other people have. What's the parallel combination? 20, 30, and 40. What do we get? Anyone? Anyone online? Any numbers? Wow. That is very loud. Okay. What do we have as the parallel combination? R5 is 9.23 ohms. I think I heard something else before, but 9 point is correct. Sorry, not this. R5 is 9.23. 10, 20, and 30. Is that correct? 1/10 plus, I'm sorry, 1/20 plus 1/30 plus 1/40. And of course, one indication is that it has to be smaller than the smallest value in that network. Remember that concept, right? And so REQ is 10.9. Oh, I can't do elementary math. 19.23 ohms. Now, once you have that, you simply apply Ohm's law. And I'm going to state this current as IS. IS comes down here, and then it gets divided into I2, I3, and I4. So if IS is being supplied by the voltage VS, it causes a voltage drop. So now that I've reduced the circuit, applied Ohm's law, I expand the circuit back up again step by step. So the next step would be IS going through all resistors. And in this case, point of entry for R1 is to the left. So what is the voltage drop sign on the left? Plus or minus? On the left. How many of you say minus? 2, 3, 4. I'm going to take -5 points off each and every one of you over the next quiz. Current always goes from high to low. Speaking up in class is not an offense. I do not penalize students. Okay. Current always goes from high to low. So point of entry for a resistor is always positive. For a supply, it goes from minus to plus. Right? For a supply, it goes from minus to plus because it's supplying. Otherwise, our equations would never balance out. So current goes from minus to plus for a supply. So it's going up. And then when it enters the resistor, it causes a drop in the voltage. Hence, sometimes it's also referred to as a voltage drop. So point of entry would always be higher than the point of exit. So you get plus and minus. And so we have a plus on the left, minus on the right. And the same thing for R5, plus up top, minus at the exit point. Again, this is all a learning process. So I don't want students to hesitate or fear to speak up in class, okay? If you're wrong, you're wrong. It doesn't matter. The important thing is you learn. See, if students keep quiet when the professor or instructor asks a question for fear or hesitancy of being wrong, then I feel that that's not a very good approach to learning. Okay, so even if you're wrong, speak up because you're going to remember that going forward. Anyway, coming back to our circuit, voltage drop across R5 has a plus up top, minus at the bottom. We call that V5 or VR5, doesn't really matter. And that voltage is across R2, it's across R3, and it's across R4. R5 is a combination of R2, R3, and R4. Voltage across parallel combination is a result of all of those resistors working together. So if it's a combined effort, same voltage, right? So V phi appears across R2, appears across R3, appears across R4. Make sense? Right? And now you simply apply Ohm's law again. I would say V5 is equal to IS times R5, and hence I2 is V5. Let me write V5 over R2. I3 is V5 over R3. And I4 is also V5 over R4. Let's take 10 seconds. You think on that. Let me know if you have any questions. Any questions? Does the procedure make sense? Does the method make sense? Right? You reduce the circuit down to one single resistance, you apply Ohm's law, and then expand it back up again step by step. Okay. So if there are no more questions, let's look at example B. Example B, you can solve using circuit analysis. You can also show this to a layperson and ask them to solve it using logic. You're driving down the street. You have two options. Both streets have some construction going on. They have some traffic. How long it takes you to traverse both streets depends on the construction and the traffic. If the traffic and the impediments are exactly the same, it would take the same amount of time to go to the other side of the street. So in this case, you have current, I'm referring to example 2. You have current source of 2 amps. Current source of 2 amps coming here. It splits in two, I1 and I2. Resistance for the first branch, what do we see? R1 and R2 are in 5 plus 15, 20 ohms. How about the second branch? 20 ohms. So we can see logically that IS splits in two, but when it splits, it's an equal split. What's the answer? 1, right? Again, as I said, you can show this to a layperson who's absolutely no knowledge of circuit analysis, and you can solve this logically. That's why I particularly like this example. Anyway, let's apply a circuit analysis technique. So the circuit analysis technique is series parallel analysis. We will reduce it to one single resistance. IS goes down 2 branches. Both branches have resistors in series. I will call these as, let's see, R1, 2, 3, 4. So let's call this as R5. Let's call this R6. Both R5 and R6 are equal to 20 ohms. And they are both in parallel as seen by the source. From the perspective of the source, R5 and R6 are in parallel. If you find REQ across the source, I mean, you remove the source and you measure REQ, what do we get? N or R, I mean, R or N. When you have N number of resistors in parallel, all with the same value R, REQ is R or N. R in this case is 20 ohms. N is 2. So 2 resistors of 20 ohms in parallel. Req is 10 ohms. You can also solve it. 20 times 20 is 400. Divided by 20 plus 20, 40, 10 ohms. So you have 10 ohms Req. Your total voltage, let's call it Vs. Vs is equal to Is times Req, gives you 2 times 10, 20 volts. And 20 volts appears across all branches of that circuit. It's a parallel circuit. So the current source also has 20 volts. The first branch has 20 volts. The second branch also has 20 volts. It's a parallel circuit, right? The voltage remains the same. You all with me so far? Then we apply Ohm's law. You can find I1 as Vs over R5, 1 amp. I2 is Vs over R6, 20 over 20, 1 amp, which is what we had earlier, right? 2 amps equal split, 1 and 1. All right, take 10 seconds. Let me know if you have any questions. Any questions? Does the method make sense? Right? The steps, the methodology, and the steps that are implemented, those are the most important. The calculation, of course, it's just a separate part. Because if your problem setup is incorrect, the calculations don't matter. So problem setup is the most important. Okay. How about C? Example C. What do we see at the far end? Series, the answer is R3 plus R4, the answer is. And then what do we have? Right? So R3 and R4 are in series, gives us 15 plus 25, 40 ohms. 40 ohms is in parallel with 40 ohms. So Req, so the parallel combination is worth 20 ohms. 20 is then in parallel with R1. Just seeing if you are paying attention. It's in series, yes. 10 plus 20 gives me 30 ohms. 30 volts being applied to 30 ohms. My current is, I thought you were still awake. 1 amp, right? 1. So again, I like these examples again because you can solve them. It's a good way to actually reinforce the material that we learn. Okay. So I'll quickly draw out the equations here. So for C, you start at the far end. That takes you to, and Req is measured here. So this is 40, this is 40, and this is 10. 10 plus 20, and therefore Req is equal to 30 ohms. Total current Is being supplied is Vs over Req, which is 30 divided by 30, 1 amp. And then we expand the circuit back up again in the exact same manner. So if you apply and you plug in the voltage source here, the same current is flowing through the circuit IS, which causes a voltage drop similar to example A, plus minus 10 volts and 20 volts. Okay, let's take 10 seconds. Let me know if you have any questions. Any questions? Does it make sense? Right? So, two more topics to look into: voltage division and current division. These are not new analysis techniques. These are shortcuts. They are shortcuts which are derived from Ohm's law. Okay. When you apply a voltage, and this example uses a source, doesn't have to be a source. This could be a separate part of a circuit that has a voltage applied across a series connection of resistances. Something like this, right? This is a series connection of resistances, and we had a voltage that we determined across that series connection. You could apply voltage division to calculate the voltage directly across each one of those resistors. So if you apply a voltage to a series network of resistors, what happens to the current? Current remains the same. It's constant, right? It doesn't change. So the current remains constant. I in a series circuit remains the same. Voltage gets divided. So voltage division principle states that when you apply a voltage to a series network of resistors, a fraction of the supply voltage appears across each resistor. And the fraction is given by the ratio of the resistor to Req. Quite a sentence, but mathematically it's rather straightforward. There's a derivation in there. I'll quickly go over the derivation, but the derivation is not something I will ask of students. Okay. Again, as I stated, it is a shortcut, and the shortcut is derived from Ohm's law. The shortcut allows you to skip a couple of steps, at least one step. What is the total current I? V total divided by Req, right? V total divided by Req. Req in this case is a series connection, so R1 plus R2 plus R3. But total current I is the total voltage divided by the total resistance. What is the voltage across each individual resistor? Current I remains the same. So from Ohm's law, what is the voltage? Individual resistor, I times R1. I, we established in the first step, is VT over Req. You plug in the values and you rearrange the terms, and you obtain V1 as a fraction of the supply voltage VT, and the fraction is given by the ratio of the resistor to Req. That's it. As easy as that. So it's a fraction of VT. Fraction is the ratio of resistor R1 to Req. Similarly, V2 is VT times R2 over Req. And V3 is VT times R3 or Req. In case you haven't yet taken a look at the final exam page, this is one of the topics I will assess, guaranteed to appear in the final exam. Not for a lot of points, just a couple of points, but it will be there on the final exam. Okay. Again, if students have not yet taken a look, I suggest you take a look at the final exam. All the topics and everything is, all the information is listed on there. Make sense? Let's take a look at an example. We have a supply voltage V total of 15 volts that's applied to a series connection of 4 resistors, 1, 1, 2, and 6. My total REQ kilo ohms, as the student pointed out in the morning section, 9 o'clock section. I'd forgotten the K. And so this is 8, 9, and 10 kilo ohms. All right, calculators out, and you tell me what the fraction is for V1. Actually, you can solve this without any calculations. What is V1? 1.5 volts. How about V4? Anyone online who is calculating? Nine. Again, you don't really need a calculator. 15 times 6 is 90. So 90,000 divided by 10,000. Therefore, V4 is 9 volts. I forgot the volts for V1. That's half a point of deduction. So always have units. Don't forget the units, especially the unit prefix also. Take 10 seconds, think over it. Let me know if anything doesn't make sense. Okay. Voltage division and current division are shortcuts. The shortcuts are derived from Ohm's law. It allows you to skip over a step in your analysis. We do not have to find the current in order to find the voltage. So it allows us to skip at least one step. Any questions? Yes. Mm-hmm. Yeah. That's right on the next slide. Yeah. Shall I move on? Okay. Then we get to current division. Current division applies to parallel circuits. In a parallel circuit, 2 nodes, so voltage always remains the same, right? The voltage that appears in a parallel network of resistors is a result of all of the resistors working together. It's a combined effort. So whatever voltage we obtain remains the same for every branch of the circuit. However, current gets divided. So in a parallel circuit, V is the same, current gets divided. So current division, again, is a shortcut. The shortcut is derived from Ohm's law. The example uses or shows 2 resistors, but it applies to any infinite connection of resistors. Okay, it doesn't matter how many you have in the actual circuit. So voltage remains the same. I will refer it to as VT. Actually, you know what? It's already given as V. The same voltage V appears across all 3 components, right? And then voltage V would be given by I total times REQ, right? And REQ in this case is the parallel combination of all the resistors in the circuit. So if I wish to find current I1 from Ohm's law would be voltage V divided by R1. V is IT times REQ. So the equation becomes IT times REQ over R1. That's it. It's as easy as that. Current division principle states that if a current is supplied to a parallel network of resistors, a fraction of that total supply current flows through each resistor. The fraction is given by the ratio of Req to R1, or Req to that resistor. The format of both equations is the same. The only thing is, for voltage division, Req is in the numerator. Sorry, Req is in the denominator. And for current division, Req is in the numerator. So the ratio is flipped. Okay. Again, keep in mind, this is not a new analysis technique. It's a shortcut that is derived from Ohm's law. So similarly, I2 would be a fraction of IT. The fraction is given by Req over R2. And then let's look at an example. So calculator's out. You tell me what Req is. 10, 30, and 60. What do we have?
Is it 6.67?
That is correct. Typically, when I have values like this, like 3.33 or 6.66, I tend to go like 4 significant decimal places. Right now, it's just 6.667. If I'm trying to solve a circuit, unknown circuit for the first time, I take as many decimal places as I can to just reduce the chances of error. Anyway, so you can do 6.67, which is fine. The point I'm making is I typically take 3 or 4 digits, but students can take, well, 2, at least 2, okay, if not longer. Anyway, so that is correct. And then I1 would be a fraction of IS. The fraction would, of course, be Req divided by R1. So what do we have? 15 times 6.667 divided by 10. What do we have as I1? Should be a nice round number. 10. 15 times 6 is 9. 9.999. 10 divided by 10. And did we get 10 amps? Does everybody get 10 amps? Now, I'll write out the equation. You can calculate the others, but you can solve them logically. Think about how you can solve this logically. Look at the values of the resistances. R2 is 3 times R1. R3 is 6 times R1. Current is inversely proportional to resistance. So the value of I2 would be 1/3 of I1. Current I3 would be 1/6 of I1. Make sense? Right? These are small things to keep in mind when you're trying to solve so that you can verify your answers as you go along. Okay. All right, let's take a 10-second pause. Let me know if you have any questions. We are ahead of time, so that's good. Now, voltage division and current division, from what I understand, is not typically covered in Physics 3, right? Okay. Again, it's classified as kind of halfway between an analysis technique. I like to call it as a shortcut. It's not a new analysis technique. It's derived from Ohm's law. It simply allows us to find voltage and current directly without finding the other quantities. Okay, shall we move forward? Okay, so then here is the meat of circuit analysis. we'll learn three analysis techniques: node voltage analysis, mesh current analysis, and superposition principle. Superposition principle is not a new analysis technique. Superposition principle is used, well, not used, is implemented by dividing the circuit, a large circuit, into multiple pieces. And then each piece is a simple circuit. You can solve that using series parallel analysis technique. But node voltage analysis and mesh current analysis are new analysis techniques. And they will use KVL, KCL to generate equations. So you have a set of linear equations with unknown variables. The unknown variables will be the node voltages and the mesh currents. And then you use those to determine the voltages and currents that are present in the circuit. Think back to chapter 1. We said, what is circuit analysis? Circuit analysis is basically the theoretical analysis that we perform to determine the values of unknown voltages and unknown currents that appear in a circuit. And so these are the two techniques that you can use to solve any circuit. Okay. So let's take a look at what node voltages are first. Voltage, this is R3, by the way. Voltage uses a two subscript notation. So we talked about two subscript notation in chapter 1. VAB means voltage measured at A with my reference at B. Right? Voltage is the electric potential difference between any 2 points. You need a point of reference. So the second subscript is minus, the first subscript is plus. Point of reference is always the second subscript. Now, we will look at a single subscript notation. Single subscript notation, where we simply use VA, VB, VC, and VD. The second point, the second subscript is implied. Okay. Second subscript is implied. And so that reference point could be any node in the circuit. So we talked about how nodes are a junction point in a circuit where two or more components are connected together. The voltages you measure at that node are the node voltages. The reference point for those node voltages, more likely than not, could be something that is indicated as ground in the circuit. It doesn't actually have to be ground. It doesn't really matter for the purposes of analysis. But as just as a separate note, ground is noted by 3 parallel lines in the shape of a triangle. Sometimes it is literally known or not noted as a triangle. Sometimes I've also seen this. And the acronym would be GND, ground. Anyways, coming back to our node voltages, whether a ground is indicated in the circuit or not, you choose a reference point of measurement for the entire circuit. In this case, we have 4 nodes, A, B, C, D. Right? This is a circuit which has 1 voltage source and 4 resistors. You are 4 nodes in the circuit. The entire bottom connection is one single node A. Keep that in mind. These are small concepts that you will need to use or keep in mind when you apply these larger analysis techniques. So you have this bottom connection. That entire connection is one single node, electrically speaking. Doesn't matter how long the wire is, electrically it is one single node. So because the circuit indicates ground, I will choose that as my reference node. It is important that the reference node could be any node in the circuit. For now, let's stick this as my reference node. All other node voltages are measured with reference to A. A is my reference node. All other voltages, meaning VB, is referring to VBA. VC refers to VCA and VD refers to VDA. And that is how you would relate the single subscript notation to a two subscript notation. The point of reference is implied. Okay, so if you say, or if you state a node voltage, more often than not, it is the ground that is present in the circuit. Now, when you're setting up the problem for analysis, you can choose any node you want. I'll wait while you write that down. So again, two subscript notation, VAB, VBC, VDA, all require a point of reference. In the node voltage analysis technique, we choose a reference node. In this example, that node is chosen as A. So all other node voltages are measured with reference to that node. That means VB, voltage at node B, is VBA, voltage measured at B with my reference at A. VC indicates it's VCA, voltage measured at node C with my reference at A, and VD indicates it's VDA, node voltage at D measured with reference to A. Okay, the second point of the reference point is implied. In your analysis, again, we are trying to generate equations, right? We are trying to generate equations for the purposes of analysis. So equations will have unknown variables. In this case, the unknown variables are the node voltages. So the less number of unknowns we have, the easier our analysis. Make sense? Right? In this case, we have 4 nodes. So there are 4 unknown variables. You can choose, for the purposes of analysis, you can choose any node, A, B, C, or D, as your reference node. It does not have to be A. You can choose any node you want. Your answers, your values for the node voltages would change. Let's say if 4 students here, let's say 25% of students choose A, someone else chooses B, someone else chooses C, and someone else chooses D, your answers will all be different because your point of reference is all different. Keep that in mind. Okay, so it doesn't matter what node you choose, your answers would be different. But when you calculate the resistor voltages, they will turn out to be exactly the same value. Your node voltages might be different, but the resistor voltages will not. You can take a single example problem and solve it multiple ways, and your answers will all be correct. So, any questions so far? So in this example, we choose A as a reference node. What is connected at A? Well, ground. Yes, ignore the ground for now. Yes. My question was incorrect. Let me phrase it more clearly. What components are connected at A? Yes, R2 and R4. How about VS? VS is also a component. Okay. So this is again an important teaching point. When we say components, a source is also a component. Okay. So we have VS, we have R1, we have R4. This is the important point. In node voltage analysis, if you have a voltage source in a circuit, always choose one end of that voltage source as your reference. Okay. If you have a voltage source, always choose one end of a voltage source as a reference node. two important reasons why. We are talking about reference node, right? What is the value of the voltage at that reference node? We're asking about VA. What is VA measured with reference to? A. So voltage at A measured with reference to A is, so when you choose a reference node, the answer for the voltage at that reference node is 0 volts. And that's why it doesn't matter which node you choose as reference. You can choose B, you can choose D, you can choose C. Whichever node you choose as reference has a value of 0 volts for the purposes of that specific analysis. Okay, for the purposes of that specific analysis, that reference node is 0 volts. So if A is 0 volts, you automatically have an answer for the node voltage at the other end of that voltage source. Because what is the other end of this voltage source? Node B. Node B measured with reference to A would be VBA measured from A to B. What is my answer? You automatically knocked out 2 of the 4 unknown variables. So VB would be equal to VS. If you choose B as your reference, then VB is 0 volts and VA would be equal to minus VS. Here's A, here's B. A is below B, so if you're looking up, it's plus VS. If you're looking down, it's minus VS. And online students can't see the hand gestures I'm making. Again, the illustration was A and B, and the distance between the two is VS. So again, if you're looking down from B, then it's minus VS. If you're looking up from A, it's plus VS. It doesn't matter. So again, to keep things simple, you might want to choose the negative end of the voltage source as your reference. That would give you a plus VS at the other end. So we have 4 unknown variables, right? We chose A as a reference, so that is 0 volts. That also gives us an answer for VB, which is VS. That leaves us 2 unknown variables, meaning I need at least 2 equations to solve for these 2 unknown variables. Make sense? Right? And so then you apply KCL and you generate 2 equations, and then we solve them, and we have our answer for node unknown variables, VC and VD. Okay, and we will see that. Actually, you know what? Still have a couple of minutes. All right, we'll stop here and we'll see that next class. Okay, we'll end class here early today. Office hours today afternoon. And also teaching the lab from 3 to 6. So if you wish to stop by during lab times, that's absolutely fine. If I have a few minutes between groups, I'm happy to answer student questions. Homework is due tonight. In case you haven't yet started, take a look at it. Let me know if you have any questions. Otherwise, I'll bid you a good day and see you all on Friday.